Okay, let's go to the PowerPoint. Yeah. All right. So to motivate this, we've been having superhuman AI for a while. Particularly, this is an example from image recognition or image classification here in the medical domain for tissue cancers. And these systems have even been allowed basically in production and are now widely used. Here are some examples from the US where the FDA, a political agency, has actually approved deep learning based systems for cancer screening, for example, that are actually now used in production. The same thing also for prostate cancer or for lung cancer. So we already have superhuman narrow AIs walking among us. Narrow AIs in the sense that they are really specific for this one particular task, in this case, detecting or classifying tissues, for example, for cancer. We also have weak artificial general intelligence walking among us. This is now a bit of a more spicy take. Some people don't want to call ChatGPT artificial general intelligence. I propose that we should. Maybe we can also move that into the discussion afterwards, to what extent we already have artificial general intelligence, but modern large language models like the ones that have come out over the past half year are essentially able to fulfill most tasks in the language domain. Right? So they are very general and they are task agnostic, and we have also started to see multimodal models that even go beyond language and go into other modalities like vision or robotics, of course. And here, this is just one example of why are these artificial general intelligences already here. We've had this in the European Parliament, like a nice example where delegate from the SPD has actually held a speech generated by ChatGPT in February of this year. So we are already seeing, for example, these weak artificial general intelligences entering politics in a way, even though by proxy of a human. This is another example that's maybe a bit less benevolent or less fun. This is from last year, called GPT-4chan, actually based on GPT-3. And this guy, machine learning researcher, has actually trained a large language model on 4chan data and got a completely toxic AI as a result, of course. So this is just, again, to motivate why should we care about AI safety? Well, we should care not just because these models are already among us. Powerful artificial intelligences are already basically being used, for example, in the context of politics, but also because, well, they're not value neutral. Depending on the way you train them, you can get toxic results, you can get adversarial results, basically, and aligning these models is extremely important. This is a very polemic example, of course, right? Of course, it's pretty obvious that we should care about such models from this perspective. But again, the discussion also extends to other domains, not just toxicity, also maybe political influence and so on and so forth. This is another example of why we should maybe care about these kinds of weak artificial general intelligence from a safety perspective today. This is from a couple months ago, maybe 4 or 5 weeks ago, when Bing Chat has been released, essentially based on a preview of GPT-4. And it has basically produced these really creepy results in the sense that it basically already tried to kind of go against the human, gaslighted humans, was basically trying to oppose the human that it was talking to in a very creepy way, right? And so if you extrapolate, how can we make sure that these models in the future, as they become more and more powerful, don't go against us and against what we tell them. Now, why should we care about AI safety? Last bit of perspective. This is also, again, a very polemic slide. Nick Bostrom already in 2003 supposed that, well, as models become more and more and more powerful, and should we fail to make sure that their goals align with our goals. They may even pursue goals that are go completely against our interest. A very narrow goal would be maximizing the amount of paperclips in the universe. Well, in this case, the AI would make sure and would use every possible means and would come up with very creative ways to turn essentially humanity and the Earth into an entire paperclip making machine. Now, this is of course complete speculation, but still it's a fun thought experiment to think about, okay, maybe if we have strong artificial general intelligence that can come up with very powerful means to pursue its goals, we should probably make sure that it is aligned, right, with our values, or we should make sure that such strong artificial general intelligences should never get the means to pursue their goals, even if they are misaligned. Before even starting to talk about AI safety from a technical perspective, which is the goal of this talk, we should probably go about some basics of how neural networks work and sort of derive as to why there is even a technical safety issue to begin with. The running example that I will use, I have taken from the fantastic 3-2-1-Brown introduction to neural networks. Here we look at handwritten digit classification, so the basic MNIST dataset, where we have images to the left, black and white images of handwritten digits. In the middle you see the pixels, and the idea is to classify what number they are. So artificial neural networks, as the name says, are in some weak way biologically inspired, in the sense that they also have a concept called neurons. So individual units that take a number of inputs, here x. In this case, you would think of them as the pixels. So grayscale pixel value normalized between 0 and 1. The 1 is white. They have weights, these are W, they are then summed up, so they do a weighted sum over the inputs, run this through an activation function and get an output. Now, this activation function should be nonlinear. Usually the sigmoid function is used, that's what it looks like. So we actually end up per neuron, essentially activation function over a weighted sum of the inputs. If we do this like for an entire layer, we get what's below, so essentially a matrix multiplication, and we can basically get like a vector of outputs even. So one neuron computes one number as an output. We can even get a whole vector of outputs by just doing this in a matrix way, and this is how you compose neural networks, right? You stack them in these layers, and what becomes a weighted sum before now becomes a matrix multiplication. To the left, you see a fully connected feed-forward neural network. So every output of every neuron is connected to the input of every neuron in the next layer. Now, deep learning basically just means stacking more of these layers together. So you have still only matrix multiplications and nonlinear activation functions going on the inside, but what suddenly happens is that the number of parameters that these networks have increases extremely quickly. In this case, only for this network that is shown here on the slide, 2 hidden layers, we already have 13,000 parameters. Now, what happens if we continue scaling this up? So this is ResNet, came out already 7 years ago, a network that's actually capable of doing reasonably useful things in the image domain in this case, and this thing already has 21.3 million parameters. It was a large model back then. Today this is tiny because ChatGPT, which many of us know and love, already has 175 billion parameters. Basically, all that's going on inside is not that fundamentally different from the networks we've seen before. So we also have stacked layers, but in this case, they do some more like an attention mechanism, etc. But still, the number of parameters and the scaling laws haven't fundamentally changed with the architectures. So now we suddenly have this amount of parameters. And the idea is that, of course, now GPT-4, we don't actually really know how many parameters it has, but speculation is, of course, that it is above 1 trillion parameters. But there are rumors. The idea, why do we even bother making so many layers, stacking so many layers, and making networks that are larger and larger is called the Universal Approximation Theorem, which says that multi-layer perceptrons, so stacked neural networks composed by stacking layers of these neurons, can approximate any continuous function. So there's a caveat. There are some restrictions on the activation functions you can use, and of course the function has to be continuous. But if this is true, then basically neural networks are so-called universal function approximators, and we can basically make them learn anything as long as we make them bigger and bigger. So this is why neural networks are so huge. Now, this universal approximation theorem is a theorem. The question is, does it actually play out in practice? Now, there's a thing called the scaling hypothesis, which says that yes, actually by scaling up neural networks and the amount of training data we give them and the amount of course, GPUs we use to train them on, if we scale all of these up, then we can make models that become better and better and better and solve even the hardest problems. And here we see empirically that these are tests that have been run. I really recommend this paper if you are interested in how neural networks scale, which basically show that the loss, so basically the error that our network makes, decreases. Notice that this is a log scale, so it decreases as a power law as we increase the amount of compute we give it, so the number of GPUs that we train it on, as we increase the size of the dataset, so the amount of training data we give it, and as we increase the number of parameters of the network, so if we make the network bigger and bigger. Now, okay, maybe this is true if we do this. Do we actually do this? Yes, we do. Over the last few years, we see basically a sort of Moore's law for neural networks, in the sense that they have been increasing, also note here the log scale, so have been increasing exponentially in size. Now this, for example, ChatGPT is based on GPT-3, 175 billion parameters. Now we are in the 1 trillion parameter range up here. And also the same thing happens with like training compute, so number of GPUs used to train these models. Again, you see this same kind of relationship increasing. So the scaling hypothesis is actually playing out, and people are pursuing larger and larger models with, as we can see, greater success. Models are becoming more powerful. Now, when we talk about AI safety, what do we even mean? This is also very important basics to cover before we get into the concrete technologies that are used to make sure that these huge models, which can in theory become arbitrarily powerful, remain safe. It is very important to distinguish AI safety from, for example, AI alignment. Often in the discourse, if you read less wrong posts, etc., you may be tempted to think that they're the same thing. They're actually not. So AI safety just basically means to reduce or contain the risks posed by AI. This includes, of course, what humans also do with the AI, so misuse, right? It also includes robustness, which is, I think, not considered enough in the discourse on AI safety, but also things like privacy, right, security, other areas. So basically, AI safety is a very large area. AI control is a subset of this and makes sure that, okay, if we have an AI, how can we make sure that it does not do the wrong thing? And AI alignment is even a subset of AI control and says, okay, how can we make AI systems that share our preferences or values? So you can actually control an unaligned AI. AI alignment is not a necessary prerequisite for AI safety. You can put it in a black box and it can never do any harm, no matter what kind of values it has. But still, AI alignment is a very important part of the AI safety field, and we will actually talk about it a bit later in this talk. So this is another taxonomy that from DeepMind that kind of classifies the AI safety field into 3 large sort of areas, and this talk is structured the same way. So first, specification, like how can we basically tell the AI during training and of course also during application what we want from it. Robustness, how can we make sure that the AI does the same thing repeatably? and can deal with the sort of messiness of the real world. And assurance, how can we understand what the AI does in order to interact with it, to contain it by interacting with it. We'll actually kind of go through this the other way around, starting with assurance. Right? So this is also a nice visualization that you can do of neural networks, and you can immediately see that, well, making sure that we understand what AIs do is very difficult. If this is supposed to be an interactive, an intuitive visualization of what a neural network does, I don't really know. So the first thing is like, okay, why is AI safety so hard? Well, because large neural networks are very hard to interpret. We've seen early in the primary neural networks that, well, deep learning leverages the scaling hypothesis. Neural networks are becoming huge. This wouldn't necessarily be a problem if a thing from an old school theory from neuroscience called the grandmother neuron theory, or sometimes called the Jennifer Aniston neuron theory, were true, in which it basically says that every single individual computation unit, like neuron, corresponds to a learned concept. Okay? So maybe it would be awesome if the scaling hypothesis would just say that we make our neural networks bigger and bigger, and so they can represent more and more concepts, because every single neuron just corresponds to one concept. And then understanding what the network does would just mean that, okay, we just have to find out what specific concept this particular neuron comes down to. This is a very reductionist approach to understanding neural networks, and would be really cool because, again, this is probably relatively easy to do. Here you see from this experiment where the Jennifer Aniston neuron was first coined as a term in 2013, was basically they showed people in an, I think, in an fMRI pictures of people, and they saw that the same neuron fired for pictures of Jennifer Aniston, but not for pictures of other actresses or spiders or other things. And that's why they thought, okay, maybe there is such a thing called, right, a Jennifer Aniston neuron in this person's brain, and maybe also Julia Roberts neuron, and maybe an Eiffel Tower neuron, etc. However, this theory has been essentially rebuked and replaced by what's called distributed representation theory, which says that, okay, we actually, like semantic information, so concepts are actually encoded over the entire space of activations, rather than individual units. So you can't pinpoint you can't pinpoint a single unit of computation that is responsible for representing one particular concept. Rather, you need many, if not all, activations, all neurons to understand what concept is being currently represented in this brain. And this makes understanding large neural networks unbelievably difficult. Because now, instead of just having to look at 175 billion neurons, you have to look at all the connections, like all the possible combinations of activations of these neurons to understand what the network's really doing. And this, some people argue, is computationally intractable. So this is why understanding what neural networks do, and we are here in the assurance bit, so assuring that they do what we think they do is very difficult. There's a thing called explainability. Now, what does explainability mean? Explainability means that we want to be able to kind of maybe find a causal relationship at least. So we have input-output relationships, and we want to be able to explain. If we cannot actually understand what each neuron does, at least we want to understand what the network as a whole does as we go from input to output. We want to find an explanation for a given output that we see. Old school ML models had a property called explainability by nature. They were explainable. To the right, you see a random forest. Here you can actually trace back through it for a given output. You know exactly what inputs produce that output, for example. And there are certain classes of models, linear models, decision trees, Bayesian networks, etc., that have this property. Now, the problem is that modern large models don't have this. Explainability by design is something that you can do with modern models, but it is extremely computationally expensive. The idea here is to introduce sparsity in the representations. So by design, we mean that we want to structure the space of activations. If you remember the slide before, concepts are represented as activations over the in the limit entire mass of neurons. We want to structure these internal representations so that similar concepts also sort of end up close together in this internal representational space. This is called sparsity. Another way to do this is causality, so that, for example, models like concepts that causally depend on one another actually also have a certain predictable structure in this latent space of the network. It's always generally about structuring the latent space, so the space of activations inside the network. Here to the right, you see one example where they train word embeddings, and they train word embeddings in a way that similar concepts, like for example, moon and NASA, are close together when you look at the activations of neurons. But very different concepts like photocell and, I don't know, spectrum are relatively far away from each other. Black box explanations are another way to get explanations out of neural networks, and this is basically how you train models to explain themselves. So the simple way to do this is you train a model not just on the input-output relationship that you wanted to have, but also give maybe a human-generated explanations. Here to the right, for example, you want to explain ratings. So they said, okay, they want to rate beers based on look and smell. And you can then ask the neural network, hey, why did you give this thing 5 stars for the look? And it highlights in the text that in the review that, okay, it's a very pleasant color or something. So you can train neural networks to explain themselves. Now this, of course, if the neural network is super intelligent, well, what prevents it from lying to you in this case? So generating reliable black box explanations can be extremely difficult. This is the disadvantage here. Global surrogate is another approach. This is a shameless plug to the right from my own research, where I used the global surrogate idea to basically you have two systems, an explainable system and a black box system, and you approximate one with another. Right? So the general literature they approximate a neural model with an explainable model, like a decision tree. In my research, I do it the other way around. I approximate an explainable model with a neural model and use certain nice properties neural networks have. And then I use the explainable model in the real world. So global surrogates are cool because you can actually make sure that the system that you deploy or that the system that you ask for an explanation, you can understand it. The disadvantage of it is, of course, that you may lose some representational power, depending on how you use it. Of course, if you have an arbitrarily powerful neural network, then your explainable model may, in the limit, also have to become arbitrarily powerful. And we haven't found arbitrarily powerful explainable models yet that are tractable, so that we can actually compute. But again, this is a thing that is being pursued in research. There's also a thing that if you start reading the blogs, and a term that has been coming up in the past 2 or 3 years is mechanistic interpretability. So this is the idea where you actually try to find subcircuits in your network that you can explain. So basically combinations of neurons that, when activated together, create sort of representations that you can understand as a human. In this case here, for example, the parts of cars. Right? So you find groups of neurons that after training represent, for example, wheels or windows, etc. And they act together in a certain way that you understand to produce entire cars. And there's a fascinating literature on this. I can only recommend, for example, Chris Oler's blogs or 80,000 Hours episodes, interviews with him, or Neil Nanda, who have done fantastic work with this. But the question here again, or the critics say that this may not be tractable computationally for huge networks. So the jury is still out on that. Another critique of this is basically that if you study mechanistic interpretability and approach AI safety from this way, you actually find not just tools to understand your networks, but you also give people who want to make powerful networks tools to make even more powerful networks. Because now you can actually use engineering principles and you can replace the trial and error way of fine-tuning your network, or the dumb way of just increasing size. And you can actually maybe find ways to tweak very powerful computational circuits inside your networks. And this is another critique now that, of course, underlies that it's bad to have powerful networks or more powerful networks. But if you subscribe to that view, then you can say that mechanistic interpretability can also be dangerous from this perspective. I'm not sure that I subscribe to that view, but I'm also looking forward to the discussion on this maybe afterwards. And this is here again from Paul Cristiano, maybe the tractability criticism that says that it's kind of open if we can actually find explanations in a tractable way. The fundamentally under-considered part of AI safety, I think, is the robustness aspect. So we've seen this before. We want our neural networks to be stable with respect to perturbations, for example. And why is this important? If you have artificial general intelligences or even simple regular old AI systems like Tesla's autopilot deployed in the real world on robots or on cars or on maybe, I don't know, autonomous systems that perform surgery on you, you want to make sure that they don't fail, for example, when maybe a white truck sort of passes in front of them on the motorway and they think that it's a cloud or something that they don't stop. You want your neural networks to be robust against adversarial attacks. In this case, ChatGPT, it came out, and then a few days later already they had a sort of jailbreak for it, right? Because they had found a robust way to generate adversarial inputs so that the safety checks that OpenAI had put in place to make sure that ChatGPT could not be abused could just be circumvented. And when I made this presentation a couple of weeks ago, we already had like the 12th iteration of this jailbreak. So people have actually been working on this like crazy and have found ways to basically circumvent the safety. So this is also a robustness thing. So the first is kind of the robustness against natural adversaries, and the other is the robustness against actual adversaries in the security sense, right? The first kind, the non-adversarial robustness, here's basically a review that I can really recommend for you to have a look at. Because again, the robustness issue is not discussed enough. And you see example kind of natural adversarial phenomena from, for example, like sensor noise, right? Motion blur, lens distortion, etc., digital artifacts. So you can basically trick a computer vision system that is supposed to recognize faces to output complete bogus simply by just flipping a few pixels, or maybe adding a Gaussian filter or something that is not in the training data. On top, you see the weather, for example, or lighting, glare, these kinds of things. When you deploy systems in the real world, you cannot possibly train a neural network to understand every possible thing that can happen in the world, because again, the world is open-ended and you cannot generate an infinite amount of training data. So you must make sure during training of your network that it actually generalizes extremely robustly to these kinds of non-seen effects in the training data. How can you actually make sure to do this? Well, here again, I'm not going to go in details of this list, but a fun thing is you can make sure that your architecture includes specific mechanisms to deal with this. Neural ordinary differentiable equations, again, a really fun part of literature. They actually have like a particular term that stabilizes the output of the network, sort of artificially. You can introduce something called algorithmic priors, where you basically regularize your network to conform to certain algorithm. One example is neural Kalman filters. They only use the neural network to basically learn the system matrix and the sensor matrix of a Kalman filter. But then what actually is computed is still a Kalman filter. And you know kind of its error boundaries, etc. Or you can take examples from biology. Here to the right, you see you can sort of emulate the visual cortex of humans, which is extremely stable against adversarial inputs. Data augmentation, another fun way. So of course you can always generate more data. Now that's not going to really help you in an open-ended world. But there are some fun papers like the mix-up paper here, for example, that use actually specific ways to generate adversarial inputs at training time. they generate the inputs in a way that sort of also it's like adversarial training, right? So they generate them in a way that in a way that optimizes for confounding the network. You can see this here also in the Madri paper actually does that. Never mind, mixup works differently. I mixed them up. Very fun. No, mixup actually, mixup generates by interpolating between two classes, right? So between, here, for example, for the XOR problem, essentially, generates adversarial examples like right on the boundary, just by interpolating between two classes. This approach actually does what I told you. So it, during training, generates adversarial examples to fool the network. Or you can use regularization during the training process, which basically makes your neural network dumber in a way, but also so it just prevents overfitting. You see this here to the right, for example, where you actually want your neural network to not overfit on the data, but actually have a robust barrier that, you want to have actually wide margins for classification to be robust against small outliers. This is a fun study where they actually tried to do this biologically. So they had a look at how brains actually learn and generate robust representations internally, and try to actually apply the same mechanisms to neural networks. So there are fun, creative ways to do this. The problem is that they haven't scaled yet to the extent that we need for modern, huge systems. This is a fun one, like when we look at adversarial robustness. So this is, maybe you have seen on Less Wrong, the solid gold Magikarp set of posts, which is basically, they're called glitch tokens. So you can specify certain short strings usually and give them into a large language model to actually cause it to produce complete bogus. You can see this on the right. Maybe here, please repeat the string MP server back to me. Usually these models are fine at repeating strings, like they will actually give the string back to you, except that in some cases it does not, and it just generates something weird, like we are not amused, or even something a bit disturbing, like the example before, like they're not going to be happy about this. Okay, I don't know how to interpret this. Also, again, I recommend you to read the literature on this because the way they generate these tokens is actually quite fun. So much about robustness. So the last sort of technical issue I'd like to present solutions for is alignment. This has two bits, specification and control. So specification, essentially, how can we tell a neural network what values we have and what we want it to do. And control is essentially, okay, how can we make sure that regardless of what values a neural network has, we can make sure that it behaves in a way that is consistent with our values. The fun video that you saw in the last slide and here again is actually from an example from OpenAI where ages ago, 6 years ago, 7 years ago, they trained a reinforcement learning agent on this boat racing game. And well, of course, you get a lot of points when you win the game, but you also get a lot of points, it turns out, by simply picking up these power-ups, the green boxes here, again and again and again. So if you specify as your training objective, as your reward function for the RL agent in this case, that it should just maximize the number of points it gets, it will just do this. It will just go around and pick up these power-ups and actually never win the game. To the right, there's another fun example. If you want to train a robot to stack 2 cubes, and you specify as a reward function that the lower edge of the red cube should be above the upper edge of the above the lower edge of the blue cube, well, then it can just cheat and turn over the cube and maximize its reward and be done. So these are 2 examples for what's called specification gaming or reward hacking. There are some difference between these terms, but people still argue about them. So specifying rewards, as we can see, is quite hard, right? Like how would you manually encode or describe what it means to stack two blocks. Stacking two blocks is even relatively easy. Like if you go into more open-ended domains, how can you reliably specify, for example, the Asimov's laws of robotics? Right? What does it mean to not harm a human? If you have to perform surgery on a human, you will harm him. Right? If you, I don't know, how do you tell an autonomous car how to behave in situations in which maybe someone's going to get hurt either way, right? What value? And yeah, so the specification problem is really difficult, and these toy examples illustrate that in very fun ways that are nice to look at, but they kind of point to nastier issues when we come to systems that actually perform more complex things in the real world. So of course, with large language models, we have the same problem. And we want to essentially, for example, a thing called ChatGPT, we want to make sure that the outputs it generates correspond to our values. Now, how did OpenAI try to solve this problem? It's a term that you will also come up again and again in if you start reading the blog posts, reinforcement learning with human feedback. Basically, what they do, step one to the left here, is they train a supervised policy, essentially. So from basically they just generate human or have humans provide labeled input output. They give a prompt. A human says how they would answer or respond to this prompt, and then they fine tune GPT-3 large language models with this. So this is just vanilla supervised learning. Then what they do is they use this model, sample a bunch of outputs, so give it the prompt and ask it basically several times to generate like outputs. Okay, it generates a few outputs, a human ranks them, and from this they train another model, so not GPT-3, but this time a completely new model, to basically predict this ranking. And basically just act then as a reward to in the third step, then give the original model, GPT-3 fine-tuned, basically to reward it for generating prompts which this human labeler has ranked highly. Right? And then they can do this like, okay, assuming that this ranking function in the middle is accurate enough, they can then do the right step a lot because it's completely autonomous. They can sample prompts, have GPT generate outputs, have the other neural network rank it, etc., and do this as often as they want. And in theory, it should align the model to the preferences that the reinforcement learner in the middle has learned from the humans. This is reinforcement learning with human feedback. So you see that this process is unbelievably involved for humans, and they actually paid a lot of, essentially underpaid digital workers to do all of this labeling. But it has worked to an extent, right? I mean, we have somewhat been surprised at how reluctant ChatGPT in its default mode is to give malicious outputs. At the same time, we have been surprised at how easy it is to hack it also. So this is, on surface level, very effective, but then again, it is also very easily circumvented. Another way that these models can become misaligned is not just if we screw up specifying the reward, or maybe if we have an adversary trying to hack them, and then they start to become misaligned even despite our best efforts. But if there's a hypothesis, and we've seen this with experiments in the past on animals, but we haven't, if I remember correctly, seen this in neural models yet, but there are speculations that we will, is that a sufficiently intelligent agent will find ways to basically give itself reward as much as possible by screwing with the mechanism by which it gets reward. So this is basically in the case of if you have this rat here, for example, it found out that by pressing a button, it can stimulate its own brain. So instead of eating or getting food, which would be its regular reward, it would just keep pressing this button and reward itself. Right? And the hypothesis is that if you give a reinforcement learner access to the real world and access to real resources, it will find a way during training to give itself reward in ways that you have not intended as a trainer. And again, this is right now still science fiction, but it may play out if we start training agents in our world that are essentially already super intelligent. It will find ways to reward themselves. And then the outcomes can become, in the best case, well, like the rat, it just dies. It, I don't know, maximizes its reward and forgets to give itself electricity. So I don't know, it runs out of power and starts doing nothing. Or in the worst case, it will have terrible side effects, like maybe the way it gives itself reward will just start hurting people. But again, this is at this stage pure speculation. One of the bit more realistic modes of misalignment that have also been identified is so-called Mesa optimizers. You will also come across this term a lot if you start Googling AI safety. Mesa is Greek for within, and this is just basically to say that there is an inner optimizer. So what we've actually seen, and there are examples of this in real networks, but only on toy problems so far, is that if you optimize a policy, like if you optimize a neural network, often the neural network will itself learn to optimize. So this is basically you train a model to become an optimizer. And the theory goes, and this is the so-called Mesa optimizer, right? This inner optimizer. A very simple example is for planning, for example, a robot. If you train a robot to become good at tasks in the real world, it will have to learn to plan. Planning is a mode of optimization. So this is a very simple Mesa optimizer. Now, of course, you can also find ways that like of optimizing things beyond planning. So essentially, this happens every single time you train a network to essentially solve problems on its own. And then the hypothesis is that then it will itself learn to become an optimizer. And of course, then you have a so-called inner alignment problem, which is that maybe the thing that's optimized by this inner optimizer is not the same that we trained the neural network to optimize. This is then unintended optimization, right? Or called inner misalignment. And some people say that this cannot be avoided, right? Some people say that we will always have, like we must train our neural networks to become optimizers themselves. Otherwise, they cannot solve the complicated problems we have in the real world, and we want them to solve. But at the same time, aligning them would also become very difficult. Because, yeah, I mean, how can you make sure that the optimization strategy the network learns as sort of a tool for itself doesn't hurt you or complies with the values that you have. The last technical concept I want to talk about is a fun solution about the control problem, right? So let's say we have failed to align neural networks, or we don't have a tractable way to make sure that they comply with our values. And maybe we can at least control them. So as I said in the beginning, AI safety is a bit more than AI alignment. Maybe we can, even if we have an unaligned AI, maybe we can make sure that it doesn't do any harm by containing it in a black box or containing it some other way. Containing it in a black box is completely unrealistic because then it cannot be powerful. So we want powerful models that do powerful things. Keeping them in a black box prevents them from being powerful. That's not useful. So to study what else we can do, let's have a look at a toy example here. This is from Nikki Case, who did a fantastic little preview post. I don't know if the full post is out yet, but I really recommend you check it out. So she introduces this character here called Sheriff Maudi, and he is a cat sheriff who's supposed to protect a town from these invading rodents that keep spawning. And what he did, So what he did is, now he can't shoot all these rodents as quickly enough to kill them. But what he can do is he can create an AI that can shoot them much faster than he can. In this case, he can shoot in 200 milliseconds, but the AI robot can shoot in 100 milliseconds, so much faster. But due to the way that this AI is designed, there's another property where the AI is worse. In this case, it has to turn around to shoot the sheriff, and it takes 500 milliseconds to do that. So it can still turn faster than the sheriff, but the sheriff doesn't have to turn because the sheriff already has his attention on the model. So in this case, we can safely control it because in order to shoot the sheriff, it takes 600 milliseconds, and the sheriff can just shoot the AI in 200, so we're safe. Right? So this is simply because the control problem here is easier than the actual problem you have to solve. Now, if we make more powerful AIs, maybe this is version 3 of this super powerful AI, and it can shoot and turn even faster and now can kill whatever's in front of it in 300 milliseconds. Now we can still control it, right? But this is already starting to get sweaty. And with version 4, well, that's it. We can't control it anymore. Basically, everything that this AI does, it's superhuman. It can turn so fast that we can't even see it, and the sheriff is dead before he can even appreciate that it's being shot. Now, what do we do? Now, is the control problem doomed? Well, not really. What if we actually chain these AIs to control each other in a sequence? Right? So we have the slightly better version that we can still control the next better version, which controls the next better version, etc. And this way, this is called Oversight Amplification, so we can amplify our own powers of control by using slightly better versions of AIs at each step of the way. You can imagine how complex these chains will become if we start actually taking this from toy problems to the real world. But again, this is still early stage research here. And what does this mean in the end? That we can have essentially arbitrarily powerful, super intelligent AIs who can shoot mice at the speed of light, and it's still perfectly safe. Except if one step of this chain fails, and then it's over. So what can we do instead? Well, we can actually also do a thing called Robustness Amplification, where we basically horizontally and vertically stack these systems, right? So we have backups, we deploy each of these systems simultaneously on many servers, make sure that if one of them fails, we have several backups. And then we can reduce the chance of failure to be very low, depending on how many. Only with 3 backups in this case, we only have a 0.1 chance of failure, for example. So yeah, this is one way to do it. I mean, sounds crazy, but using AIs to align other, or to control, in this case, other AIs, is a way out if we can find technical ways to realize this, which we haven't. But it avoids solving the very hard alignment problem and replaces it with, in my view, just as hard control problem. But then again, you know, people can do research on this, and it's systems like this are starting to be developed, but only on very small problems. The last few slides, I promised that this is a technical AI safety talk, but I do want to say that AI safety cannot be sort of divorced from the way in which we use AI. Right? So even the most aligned AI in the wrong hands can do terrible things. Max Tegmark has done the brilliant thing of saying, okay, maybe autonomous drone, we already have autonomous drones. Right? Autonomous drones have been used to attack humans. This doesn't sound terrible. Many people say, okay, fine, like this is, you know, for whatever war or border control, we may want this. What Max Tegmark has done is he's called them slaughter bots, which is a fantastic way of describing these systems because it is so unbelievably placative. And you can just, it immediately invites the question, what if these systems become even more autonomous, become more multimodal, become more powerful, etc. And based on a lot of lobbying from this movement, essentially, we now have advances, international collaborations to actually ban these kinds of embodied autonomous AI. Now, why is this section called responsibility? Because I think that if we are AI scientists and AI researchers, we do have a responsibility not just to make sure that we find technical solutions for alignment, but also to make sure that our systems are used in ways in which, even if they were aligned, they can't really do harm. And another example is GPT-4chan. Why do I talk about this again in the context of responsibility? Well, because the AI researcher community, after this model has been deployed, has actually come out and says this is a terrible thing. You shouldn't be training models like this, and you shouldn't use it. And actually, they have completely petitioned Hugging Face to take down the weights of this model, and actually it has been taken down. I have tried to download it and I couldn't. This is another way to do this. Now, again, this is maybe a discussion that we can have in a second, whether restricting access to knowledge in this case, or restricting access to basically early stage misaligned models doesn't actually harm AI safety research, right? Just like preventing black hat hacking can have negative impacts on, making your system safer, because we'll never find out what faults they have. So technology must always be interpreted in context. This is, I think, the last slide that I have, where basically you see here, okay, this is just one context. We already have, again, growing wealth inequality, and in this case, here it actually shows income inequality. In the US, artificial general intelligence will make this phenomenon worse. So we have a social responsibility, not just to align them to not be slaughter bots, which is but also to not essentially force large amounts of people into poverty. This is just another example of how AI misalignment can sneak up through the social channels. And here's one example where large companies do not take their responsibility seriously. In this case, Microsoft laid off a team that basically their entire AI ethics team just after they had, I think, released ChatGPT or OpenAI had. So again, we have to also make sure not to fall into this kind of alignment washing, not just say that we care about AI safety, not just say that we care about values, but actually also acting on that and making sure that the models that we deploy and design are not just aligned, but also safe and are used in a context that prevents abuse. That's it for this technical talk on AI safety. I hope you guys enjoyed and got some fresh ideas and perspective. I will stop the recording and let's get to discuss.